In this video, we derive four formulas that we're going to use frequently throughout the rest of the semester. They are the Laplace transforms for 1, e to the at, t, and t to the n. After we derive these, we're just going to apply the formulas. You'll have these formulas in your table of Laplace transforms when you are taking quizzes or exams over this material. So it's not necessary to memorize these derivations, but I would like you to see the derivations at least once so that you know where those formulas come from. So just recall that if you have a piecewise function, piecewise continuous function f of t, the Laplace transform of that function is f of s, and that's the integral from 0 to infinity of e to the negative st times f of t dt. So if you're taking the Laplace transform of a function f of t, you just substitute that into this integral, and then you evaluate this improper integral. So I want to evaluate this expression for f of t equals 1, f of t equals e to the at, f of t equals t, and then f of t equals t to the n, because we're going to be using those a lot this semester. So let's take the Laplace transform of 1 first. The Laplace transform of 1 is the integral from 0 to infinity, e to the negative st times 1 with respect to t. All I'm doing is substituting, and then I evaluate this improper integral. Now remember, every improper integral is actually the limit of a proper integral. So we always have to start by writing the improper integral as a limit. The issue happens in that upper limit, so we're going to replace the upper limit with b, and then we'll keep everything else exactly the same. And then we'll take the limit as b goes to infinity of this proper integral. So we are following this process. We're going to substitute 1 for f of t, and then we write the improper integral as a limit. And then every time you're evaluating an improper integral, after you've written it as a limit, you evaluate the proper integral that's there. And you'll do that using the fundamental theorem of calculus. So I'm bringing this limit down so that these are actually equal to each other, but I'm really ignoring it right now and I'm focused on this. The first thing we do when we're evaluating an integral is we take the antiderivative. This is e to the negative st. So we're thinking here of t as our variable, and s is a constant in this context, at least until we're done. So when I'm anti-differentiating, I'm thinking of this as e to a constant times t. The antiderivative of e to the constant times t power is e to the same power divided by that constant. If I were taking the derivative of this with respect to t, I'd multiply by the derivative of the inside, which is negative s. Since I'm taking the antiderivative, I divide by that constant, negative s. And then we evaluate from t equals 0 to t equals b. And I will factor out that negative 1 over s. At t equals b, we have e to the negative sb. And at t equals 0, that's e to the negative s times 0, or e to the 0, which is 1. And then we have this here. Now, if s were negative, then I'd have a negative number times a negative number, which is a positive number. And this would be e to a positive power if s were negative. And then as b goes to infinity, this would go to infinity. But if s is positive, then negative s times b will be a negative number when b is going to infinity. So if s is positive, as b goes to infinity, this expression will go to 0 because this will be e to a very large negative power. So the Laplace transform of 1 is the value of this limit. which is negative 1 over s times negative 1, which is positive 1 over s. So the Laplace transform of 1 is 1 over s as long as s is greater than 0. Now, most of the time when we are using the table of Laplace transforms, we don't worry about that little restriction on s. But that restriction on s was necessary in order for us to evaluate this limit. So you plug in your f of t, you write the improper integral as a limit of a proper integral, then you evaluate the proper integral using the fundamental theorem of calculus, and then you have to evaluate that limit. Of that f of b minus f of a. Now, if you are a little rusty on your calculus 1 or calculus 2, some of this may not make sense. So you might want to go back to reviewing your improper integrals if you're not comfortable with this step from here to here. Most students are usually comfortable going from here to here after a little bit of review. If you don't remember how to evaluate integrals, you might want to go back to calculus 1 and calculus 2 materials and review how to compute those antiderivatives. And then this part is one of the parts that really trips a lot of students up. If you don't remember how to evaluate limits at infinity, which was studied in calculus 1, you may want to brush up on that as well. So it turns out that the Laplace transform of 1 is 1 over s, and we found that by using this process. Now let's take the Laplace transform of e to the at, because that's another one that's going to come up a lot. Now, in order to simplify this, I will add the exponents, but I think I'd like to add the exponents and factor out a negative 1 and factor out a t. So this is actually equal to negative s minus a times t in that exponent. And if you're not sure that that's equal to that, you should distribute. If you distribute the negative 1 and the t, you're gonna get negative s times t, which is right there. And then a negative times a negative is a positive a times t is right there. And then we're adding the exponents because x to some power times x to a different power is x to the sum of those exponents. The same is true if the base is e. So it's just a little bit of algebra. And now we're here, but again, this is an improper integral, so we need to write it as a limit of a proper integral. So this is the limit as b goes to infinity of the integral from 0 to b of e to the negative s minus a times t with respect to t. So we plugged in our e to the at, then we simplified, and then we wrote the improper integral as the limit of a proper integral. Okay, and then you want to evaluate the proper integral using the fundamental theorem of calculus. Okay, so I'm sort of ignoring this limit as b goes to infinity, but it's really important that I keep it there just to keep everything equal. But I'm just sort of bringing it along for right now. The next thing we would do is take the antiderivative of this. So this is e to a constant times t. The antiderivative of e to a constant times t is e to a constant times t divided by the constant. It's really just this rule. If you have the antiderivative of e to the kx, we would say e to the kx divided by k or multiplied by 1 over k plus c. That's all I'm doing here. But my k is this negative s minus a. So that's my antiderivative. And then we're evaluating this from t equals 0 to t equals b. Remember, these are bounds for t, not s. They're bounds for whatever that variable of integration is. And then I would factor out the negative 1 over s minus a. And then substitute in t equals b. And then when t equals 0, we substitute in that as well. This is our f of b minus f of a from the fundamental theorem. When t equals 0, this is e to the 0, which is 1. And then we'll evaluate this limit. And you're basically going to use just calculus 1 methods. Okay, now if s minus a is positive, this is e to a large negative power as b goes to infinity. So this will be 0 as long as s minus a is positive. So we will have negative 1 over s minus a times negative 1, which is positive 1 over s minus a, under the condition that s minus a is positive. So that is telling us that the Laplace transform of e to the at is 1 over s minus a when s minus a is positive, which means that s is greater than a. Okay, so we've proved that limit, or that Laplace transform has this form. Now, in practice, we don't do this every time. Whenever I see the Laplace transform of e to the 5t, I just say that's 1 over s minus 5 because of this rule. But this rule comes from this application of the definition. So we're going to have a table of Laplace transforms, and it says the Laplace transform of 1 is 1 over s, the Laplace transform of e to the at is this, and we're just deriving some of those using the definition now so that you know where those formulas come from. Let's apply the definition to f of t equals t this time. That I will write as an improper integral as well, or excuse me, I will write the improper integral as a limit as well. Since the limit is b goes to infinity of the integral from 0 to b of t times e to the negative st with respect to t. Okay. Now, since I've got an exponential function times a polynomial function, the best method for anti-differentiation here is integration by parts. And I would use tabular integration because I've got u as a polynomial here. So I'd let u equal the polynomial and dv equal everything else, and then use tabular integration. So u is t, dv is e to the negative st, and then we want to differentiate in this column until we get 0. The derivative of t is 1, the derivative of 1 is 0. Then we want to anti-differentiate in this column until we get, we catch up with the 0. So we want to have the same number of rows in both columns. The antiderivative of e to the negative s times t is e to the negative st, and then we would divide by a negative s, so it's multiplying by negative 1 over s. And then we would do the same thing again. So that would become a positive 1 over s squared. And then we have this sign convention. You're going to multiply across that diagonal and add, multiply across this diagonal and multiply by negative 1 and add, and that will be the antiderivative of this guy. So we have the limit as b goes to infinity of negative 1 over s times t times e to the negative st. I'm factoring out that e to the negative st now. Plus 1 over s minus, or plus 1 over s squared times e to the negative st times a negative 1. So it's going to be minus 1 over s squared times e to the negative st. And we're evaluating this from t equals 0 to t equals b. So we compute our antiderivative. Now we're evaluating the proper integral. And that requires computing an antiderivative and then using the fundamental theorem of calculus. So we plug in the upper bound and lower bound and subtract. And this is what we get. At t equals b, we're going to have negative 1 over s times b minus 1 over s squared times e to the negative s times b. I'm going to write that as e to the positive s times b in the denominator because I know it's coming. If you didn't know what's coming, then you could still get to this step. We'll talk about that in a moment. So that's evaluated at t equals b. At t equals 0, this is going to be 0, and we'll have a negative 1 over s squared, and this will be an e to the 0. So we're subtracting a negative 1 over s squared. So that means we're adding 1 over s squared here. And we have to take the limit of this as b goes to infinity. Now, as b goes to infinity, the numerator here goes to negative infinity because we're thinking of s as a constant. And if s is positive, the denominator also goes to infinity. So this would be a negative infinity over infinity indeterminate form if s is positive. If s is negative, well, in that case, this expression, if I'm replacing the t with a b, would go to infinity, and I'd have a negative infinity times positive infinity, which would be negative infinity. So if s is negative, this whole thing goes to negative infinity, and we can't evaluate the limit. The limit does not exist. But if I want the limit to exist so that I can actually take the Laplace transform of t, s would have to be positive. In that case, this is infinity, and this is going to infinity, and this is going to negative infinity. So we have a negative infinity over infinity indeterminate form. Now, if you're saying to yourself, why did you put that in the denominator? It's because I wanted that infinity over infinity indeterminate form so that I could use L'Hopital's rule. Now, if you don't want to do that, if you didn't know to do that or didn't think of doing that, you would still end up in the same place, because what you'd have is something that's going to negative infinity times something that's going to 0. So you'd have that negative infinity times 0 indeterminate form, which you would know that you have to rewrite as a negative infinity over infinity indeterminate form so that L'Hopital's rule can be applied. Okay, so that's where you would end up either way. All right, so now we're here and we'd like to evaluate this limit. That requires using L'Hopital's rule. So according to L'Hopital's rule, the limit of this is the same as the limit of a similar expression. You just take the derivative of the numerator and the derivative of the denominator, and you take that limit instead. So this is what we'll get. We'll have negative 1 over s in the numerator and an s times e to the sb in the denominator. That first one is due to L'Hopital's rule, and that second one is just the limit of the sum is the sum of the limit. So I'm just sort of keeping that around. And now as b goes to infinity, the denominator approaches infinity. So we've got a constant over something that's very large. So the whole fraction is going to be very small. So this will go to 0 as long as s is positive. And we get 1 over s squared here. So we have just shown that the Laplace transform of t is 1 over s squared as long as s is greater than 0. Now you might wonder, what happens if we have a t squared or a t cubed or t to some other power? Well, in all of those cases, if I had a t squared, I would do the same thing. If I had a t cubed, I would do the same thing. For every single one of those cases, for any t to the n, I would use tabular integration by parts. And after using tabular integration by parts, I would factor out the exponential, and I would end up with something that looks like this. After plugging in b and 0, I would end up with something that looks like this. And then as b goes to infinity, this expression in the beginning will always approach 0 because exponentials grow faster than polynomial functions. And then we would just end up with this term over here. I want to figure out what that term over here would have to be for a t to the n. Now, in order to do that, we're going to have to think through this integration by parts process for different values of n. So this is n equals 1. When n is equal to 1, I have 3 rows here. I had to take the derivative twice. And I had to take the antiderivative twice so that we had 3 rows when n was equal to 1. If n was equal to 2, I would have 4 rows, right? Let's see what would happen if n is equal to 2. And then let's think through what would happen in general. I've just got t to the n times e to the negative st dt. And I'm just wondering, what is the value of that integral in general? Well, let's look at n equals 2. When n is equal to 2, I'm going to use tabular integration. And I'll have t squared, then that derivative, the derivative of that, and the derivative of that. I have 4 rows when n is equal to 2. I had to take the derivative 3 times. And that means in this column, I have to take the antiderivative 3 times. Okay, let's see what happens when n equals 3. You guys start to see the pattern already? I hope you do. When n equals 3, I'll have a t cubed here. And I'll take the derivative as many times as necessary. So I took the derivative until I got to 0, and then I took the antiderivative. So I had to take the derivative 4 times when n was equal to 3, and I had to take the antiderivative 4 times. So the question is, well, what's the pattern? If this is equal to n, I think I'm going to have to take the derivative n plus 1 times, because when n is 2, I had to take the derivative 3 times. When n is 3, I have to take the derivative 4 times. And I think it makes sense that I have to take the derivative n plus 1 times, because if I take the derivative n times, I end up right here where I end up with that constant. And then if I take the derivative 1 more time, then I end up with this 0. So yeah, I think that's what's going to happen. Now let's actually look at the result of the integration by parts for each of these. If I factor out the e to the negative st, what I end up with is a negative 1 over s times t squared. I think I'm going to factor that negative out as well. And then I have a positive, or a negative 1 times 2t over s squared. There. And then I've got 2 times a negative 1 over s cubed. If I factor out the negative, I'll have this. And that's plus c. So I end up with this times this times this. And if I factor out the negative from all of those, and I factor out the exponential from all of those, I get this. So I end up with this polynomial in t times an exponential. As t, or if I replace the t's with b and I let b go to infinity, this is going to go to infinity, and this is going to go to 0. So it's going to be an infinity times 0 in determinate form times a negative 1. I think the same thing is going to happen there. When I multiply these two guys together, and I multiply these guys together, and then these guys, and then these guys, I'm going to have a negative term, a negative term, a negative term, and then a negative term. Let's factor out a negative from everything. And over here, we'll have t cubed over s plus 3t squared over s squared. And I've got a minus 6t over s cubed. And then a minus 6 over s to the 4th. And if we take out those negatives, we end up with that. Factor that negative out. And I'm factoring out the exponential as well, plus c. And if I replace t with b, and I let b go to infinity, Well, I'm going to have a polynomial in b here and e to the negative sb here. As long as s is positive, this is going to go to infinity and this is going to go to 0. So it'll be infinity times 0 in determinant form. And the limit of that will end up being 0 because polynomials or exponentials actually grow faster than polynomials. And we're going to put the exponential in the denominator and use L'Hopital's rule. Okay, so then the question becomes, what about t to the n? Let's go back to our derivation of the Laplace transform of t to the n with all of this in mind. Well, first I'm going to write it as a limit. So this is the limit as b goes to infinity of the integral from 0 to b of e to the negative st times t to the n dt. And then we want to use integration by parts for that piece. So there's my u. I'm making these columns really long just in case. U is the polynomial, dv is everything else, and we sort of ignore the dt. And then we're going to differentiate until we get 0. So we'll have n times t to the n minus 1. Then we'll have n times n minus 1 times t to the n minus 2. And we're going to keep going until eventually we end up with n factorial times t to the first. Because you're going to have n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And then you're going to have n factorial times t to the first. The derivative of that is n factorial, and the derivative of that is 0. And don't let the factorial, don't let it bother you. That factorial is just a constant for a particular value of n. So n factorial in this case for n equals 2 is just 2. N factorial in this case for n equals 3 is 3 times 2, which is 6. So you've got that 3 factorial times t, and then you've got the 3 factorial here. In general, we're going to have n factorial times t, and then we'll have n factorial there and a 0. And then the question becomes, well, what is this term going to look like at the end for this antiderivative of e to the negative st? Well, every time I antidifferentiate, I end up multiplying by another negative 1 over s. So I end up with a positive 1 over s squared times that over here. And we're going to keep going. The question is, how many times did we end up doing that? Well, when n was equal to 2, we differentiated 3 times, and we antidifferentiated 3 times. So I actually multiplied this by a factor of negative 1 over s 3 times when n was equal to 2. So it was 1 more time than our n value. So I think I have to multiply by negative 1 over s n plus 1 times. Let's make sure that that works over here. When n is equal to 3, did I have to multiply by negative 1 over s 4 times? Yes, that's exactly what I did. Because in order to get from t cubed down to 0 when I'm differentiating, I have to take the derivative 4 times. Take the derivative once and twice, and 3 times gets us down to a constant, and then we take the derivative 1 more time to get to 0. So if I take the antiderivative over here, I'm going to have to multiply by negative 1 over s, negative 1 over, or I'm multiplying by negative 1 over s, n plus 1 times. That means the one before that is negative 1 over s to the n times the exponential. And the one before that is negative 1 over s to the n minus 1 times the exponential. And then we're doing this plus minus convention. And it's always going to look like that. Well, actually, I'm not sure about these signs at the end, because those signs at the end are going to depend on the value of n over here. But notice that for this one, I always end up with negative terms. This times this is negative, this times this is negative. this times this is negative. After we multiply by the signs, the same thing happens here. We've got a negative here, a negative here, a negative here, and a negative here after multiplying by that plus or minus 1. The same thing should happen over here. So it's going to be negative, positive, negative if this n plus 1 leads to a negative out front here, because we always end up with a negative result. We'd have a negative value here if n plus 1 was odd, which would mean n is even. So this would be the signs if n is even. These would be the signs if n is odd. But now we're going to multiply across these diagonals, right? And then factor out the -1 and factor out the exponential. And then we'll substitute in b and 0 and subtract and then take the limit of the result in order to find the Laplace transform of t to the n. So we end up with a -1 times t to the n over s. And then we'll have negative or plus n times t to the n minus 1 over s squared. And then we're going to have n times n minus 1 times t to the n minus 2 over s cubed. Notice that when you add these exponents together, the n and the exponent in the denominator here, you get n plus 1. This plus this is n plus 1. This plus this is n plus 1. This plus this is n plus 1. Eventually, you're going to end up with an n factorial times t to the first over s to the n. That's from this guy. And then you're going to have, that's an n factorial. Then you'll have an n factorial over s to the n plus 1 here times the exponential e to the negative st. I've sort of run out of space. But that's what you'll get after you do the integration by parts. Now, if you plug in b to all of this, you end up with an nth degree polynomial in b times e to the negative sb. And I think I need more space, so I'm going to use another sheet of paper. So I have negative t to the n over s plus n times t to the n minus 1 over s squared, and so on. Then you eventually have n factorial times t over s to the n, and then n factorial over s to the n plus 1 times the exponential, which I'm going to write in the denominator. And we evaluate from t equals 0 to t equals b. At t equals b, this is what we get. Oops, b to the n over s. And then we're going to subtract this expression evaluated at t equals 0. But at t equals 0, oops, I guess we need to factor out that negative as well. At t equals 0, we're going to have a negative times a negative, which is going to make that positive. And then all of these guys are going to be 0, and all we're going to have is that n factorial over s to the n plus 1, all divided by e to the 0, which is 1. So then the question becomes, what happens to this expression as b goes to infinity? Well, this is an nth degree polynomial over an exponential, so that makes it a negative infinity over infinity indeterminate form. This is provided that s is positive. If s is positive, this is going to infinity, and this is going to infinity if we disregard that negative sign. If s is negative, then we have something that is approaching infinity over something that is approaching 0. If s is negative, this whole thing is going to infinity. But if s is positive, this whole thing is approaching or is in infinity over infinity indeterminate form times a -1. But we know that if we wanted to apply L'Hopital's rule to this, since this is an nth degree polynomial, all we'd have to do is take the derivative n plus 1 times. When we take the derivative n plus 1 times, eventually we're going to get down to a constant, or actually just take the derivative n times. You're going to end up with a constant over here times, or over s to the n times e to the s times b. So this is going to go to 0 because if we applied L'Hopital's rule n times, we would eventually get to a point where we have a constant over something going to infinity, so we would get 0. Or you can think of it this way: exponentials grow faster than polynomials. They always grow faster than polynomials eventually. So this guy is going to go to 0. And I'll just say by L'Hopital's rule. And so we get n factorial over s to the n plus 1. And this is only true when s is positive. So the Laplace transform of t to the n is n factorial over s to the n plus 1. So now we have 4 Laplace transforms. We have the Laplace transform of 1 as 1 over s. We have the Laplace transform of e to the at. Oops. That's 1 over s minus a. Laplace transform of t to the first turned out to be 1 over s squared. And that's just a special case of this one, the Laplace transform of t to the n, where n is a positive integer, is n factorial over s to the n plus 1. So we can use these now to take Laplace transforms of, say, something that looks like this. Maybe you want to take the Laplace transform of 5 minus 2 times e to the negative 3t plus t cubed minus 4t squared. Well, because the Laplace transform is a linear operator, you can just take the Laplace transform of each piece. You can factor out those constants. The Laplace transform of 5 you can think of as 5 times the Laplace transform of 1. Laplace transform of 1 is 1 over s, so the Laplace transform of 5 is 5 over s. Then we're subtracting 2 times the Laplace transform of e to the negative 3t. Well, a in that case is negative 3, so just by using pattern matching, the Laplace transform of e to the negative 3t is 1 over s minus a negative 3, so that's just 1 over s plus 3. Then we're adding the Laplace transform of t cubed, so that's going to be 3 factorial over s to the 3 plus 1, so that's 4. And then we're subtracting 4 times the Laplace transform of t squared. That's 2 factorial, or I said t squared. I think I said 3 squared, but I meant 3 squared, but I meant t squared. Of 2 factorial over s to the 2 plus 1. So that's 2 cubed. So I have 5 over s minus 2 over s plus 3. 3 factorial is 6. And then I've got 2 times 4 is 8 there. And that's the Laplace transform of that expression. Now we can also go backwards with these. The inverse transform of 1 over s is 1. The inverse transform of 1 over s minus a is e to the at, and so on. The inverse transform of 1 over s squared is t, and the inverse transform of n factorial over s to the n plus 1 is t to the n. So now that we have these 4 rules, we can take the Laplace transforms in the forward direction, but we can also take the inverse transform of functions of s like this. So maybe we'll have 2 over s minus 5 plus 8 over s to the 5th minus 2 over s cubed. plus, I keep using 5. Let's do 7 over s. Well, we can factor out each of those constants. So this is 2 times the inverse transform of 1 over s minus 5. And this is 8 times the inverse transform of 1 over s to the 5th. Minus 2 times the inverse transform of 1 over s cubed. Plus 7 times the inverse transform of 1 over s. Now this one I have a rule for, and this one I have a rule for. Here a is 5, so this is just e to the 5t. And here the inverse transform of 1 over s is just 1. Now these don't quite match this form, but they have that same formula. You have to identify n from this. So if n plus 1 is 5, that means n has to be 4. And if n is 4, what that means is I need a 4 factorial in the numerator. Now we can put a 4 factorial in the numerator as long as we also divide by 4 factorial out there. And the same is true for this one. In this one, I've got n plus 1 is equal to 3. So that means that n is equal to 2. So that means I need a 2 factorial in that numerator. Actually, I already have a 2 over there, so I'll just pull that inside. So I've got a 2 factorial over a 3 or s cubed there. And now that matches this pattern exactly. And now this matches this pattern exactly. So we can apply the inverse transform. So we'll have 2 times the inverse transform of 1 over s minus 5, which is e to the 5t. And then we've got 8 over 4 factorial. So that's 4 times 3 times 2. So the 4 and the 2 reduce with the 8, and you end up with a 1/3 times this, the inverse transform of s to the, or 4 factorial over s to the 5th. That's going to be a t to the 4th because n is equal to 4 there. Here we're subtracting, oops, that should be an inverse transform. The inverse Laplace transform of 2 factorial over s cubed. So n is 2, so that's going to be a 2 or a t squared. And then we'll have 7 times 1, which is just 7. So we end up with 2 e to the 5t plus 1/3 t to the 4th minus t squared plus 7. And that is the inverse transform of this function that we started with. So we just derived all of these rules that will allow us to take Laplace transforms of terms that look like this and inverse transforms of terms that look like this. But all of these rules come from application of that formal definition and a little bit of calculus 2 and calculus 1. We had to remember a little bit about improper integrals as well as L'Hopital's rule and how to generalize something like tabular integration in order to derive this expression right here.